Hello, my name is Shikib Mehri, and I'm excited to present our work on Gensf, simultaneous adaptation of generative pre-trained models and slot filling. This work was done with my advisor, Maxine Eskenazi. Large-scale pre-trained models have transformed NLP research. Rather than designing complex, task-specific architectures, the dominant paradigm has shifted to large-scale pre-training, followed by fine-tuning on a downstream task. This pre-train and fine-tune paradigm has been extremely successful and has resulted in significant improvements on a variety of tasks. Often, only minor modifications are made to the model architecture prior to fine-tuning on a downstream task. For example, to use BERT for the task of intent prediction, a reasonable approach may be to just add a linear layer on top of the BERT output. However, by making minor modifications and reusing the same model for many different tasks, we are assuming that the underlying pre-trained models possess a degree of generality that allows transfer to a variety of tasks. We believe that this assumption is limiting. That is not to say that it is not an effective strategy, but more so to suggest that we can do better. Pre-trained models have certain capabilities, and downstream tasks have specific requirements. In order to get the most out of the pre-train and fine-tune paradigm, we need to achieve stronger alignment between the capabilities of the pre-trained model and the requirements of the downstream task. Both the pre-trained model and the downstream task have certain properties that can be manipulated and modified to achieve stronger alignment. In the pre-trained model, we have the architecture, the pre-training task, and the inference algorithm. In the downstream task, the properties include the data representation and the task formulation. To achieve better alignment between the model and the task, we would like to first adapt the model to the task. This can be done by modifying the properties of the model to incorporate inductive biases that are motivated by the properties and the requirements of the downstream task. Similarly, we can adapt the task to the model by modifying the properties of the task in order to incorporate inductive biases which are motivated by the capabilities of the pre-trained model. By simultaneously adapting both the task and the model, we can achieve a stronger alignment between the pre-trained model and the downstream task. With the stronger alignment, we can better leverage the pre-trained models for a downstream task. In this paper, we aim to address the task of slot filling using a generative pre-trained model. Specifically, we use the Dialog-GPT pre-trained model. Dialog-GPT has been pre-trained on open domain dialogue data. It exhibits high-quality response generation through autoregressive generation of language. We address the downstream task of slot filling, which has the following properties. The goal of slot filling is to extract a span of continuous text from an utterance in order to fill a slot. Slot filling has a fixed set of slots, and the utterances originate from human-human dialogues. So what properties of the model and the task can we leverage to create inductive biases? We know that Dialog-GPT is capable of high-quality response generation. This means that it can generate meaningful responses and that it may have implicit knowledge of certain slots. For example, Dialog-GPT might be able to understand what a first name is or what a date looks like. The task of slot filling has certain constraints that we can leverage. First of all, slot values must always be a contiguous span of words from the utterance. We also know the set of possible slots beforehand. So how do we go about the simultaneous adaptation of Dialog-GPT and slot filling? To adapt the task to the model, we leverage the fact that Dialog-GPT is good at response generation. We reformulate the task of slot filling as response generation. To adapt the model to the task, we incorporate inductive biases into the architecture and inference algorithm that take advantage of the fact that the slot values must come from the text. To do this, we incorporate a copy mechanism, constraint decoding, and a post-processing algorithm. Combined, these modifications give us the Gensf model. Next, I'm going to explain these modifications in more detail. To adapt the downstream task to the capabilities of the pre-trained dialogue GPT model, we reformulate the task of slot filling as response generation. Concretely, given an utterance, we generate a partial dialogue with each one of the slots. For example, given the utterance on the slide, we consider the date slot key. We then create a dialogue that ends in the partial system utterance, okay, the date is. Dialog GPT is then tasked with completing the utterance by generating the appropriate value for the date. For slots that are not provided in the utterance, for example, time or first name, we would expect Dialog GPT to indicate that. In the second example Dialog GPT should generate, okay, the time is not provided. In some cases, there may be additional information associated with the utterance. For example, the set of requested slots. We account for this in our reformulation by prepending a system utterance to the dialog. In this example, the first utterance is a system utterance that asks, what is the first name, last name? We know that in the task of slot filling, the slot values must be a continuous span of words from the utterance. To account for this, we incorporate a copy mechanism into the Dialog GPT architecture. Concretely, this copy mechanism first generates a probability distribution using a linear classifier. It then generates a probability distribution by attending over the user's utterance. Given these two probability distributions, we then perform a weighted sum to obtain a final distribution over the vocabulary. To further enforce that slot values come from the user utterance, we incorporate constraint decoding at inference time. Constraint decoding limits the vocabulary during generation. Since Dialog GPT was pre-trained on open domain data, it may generate arbitrary continuations of a response. To focus the generation and ensure that a valid slot value is produced, we constrain the vocabulary at inference time to only the tokens that are present in the user's utterance. Because Dialog GPT operates on subword tokens, it may sometimes generate somewhat correct answers. For example, if the user says their name is Lakesha, Dialog GPT may incorrectly output that the user's name is Lakeha. To mitigate this problem, we apply a post-processing algorithm that uses the Levenstein distance to find the closest span of words in the utterance to the generated slot value. These four modifications make up the GenSF model. These modifications aim to simultaneously adapt the pre-trained Dialog GPT model and the downstream task of slot filling. We carry out experiments on two datasets. The Restaurant 8K dataset covers the domain of restaurant reservations. The DSDCA data includes 4 different domains: buses, events, homes, and rental cars. We evaluate our model in several experimental settings: full data, the few-shot setting, and the zero-shot setting. This table shows the full data and few-shot results. We show the F1 scores on the Restaurant 8K data at various fractions of the dataset, ranging from 100% of the data to 1/128th of the data, which is only 64 training examples. We compare GenSF to SpanBERT and Convex. Prior to GenSF, Convex was the best performing model on the Restaurant 8K data. The first thing I want to highlight is the performance of GenSF compared to SpanBERT. SpanBERT fine-tunes BERT to extract a continuous span of words from the utterance. GenSF significantly outperforms SpanBERT at all fractions of the training data. The most significant improvements are in the extreme few-shot settings. Specifically, at 1/16th of the data, GenSF achieves a 13 F1 score improvement, and at 1/128th of the data, GenSF achieves a 42 F1 score improvement over SpanBERT. The Convex model designed a pre-training objectives specifically tailored to slot filling, making their pre-trained model much better aligned to the downstream task of slot filling than SpanBERT. We achieved moderate improvements over Convex, despite the fact that we did not rely on large-scale pre-training that was specifically designed for slot filling. Instead, we achieved better alignment by adapting the task to the pre-trained model in addition to adapting the model to the task. The most significant improvements over convex occur in the extreme few-shot settings. For example, with 1/16 of the data, Gensf achieves a 3F1 score improvement over convex. This slide shows the result on the DSDCA data. For each of the 4 domains in the DSDCA data, we report results in the full data setting and the few-shot setting, which is 1/4 of the full data. Gensf achieves strong improvements in the buses and events domains, in both the full data and few-shot settings. Concretely, we achieve a 2 to 4 F1 score improvement in these domains over convex and more significant improvements over span-BERT. Though our performance in the homes and rental car domains is still competitive, it is nonetheless lower than the other models. One of the motivations in reformulating the task of slot filling as response generation was that the dialogue GPT model may have implicitly learned the meaning of some slots. This motivation is validated as Gensf can accurately predict slots like time and date without much training data. However, this is not true for all slots. Gensf may underperform on slots that are ambiguous, ill-defined, or unlikely to have been observed during open domain pre-training. Future work can potentially mitigate this by further pre-training the dialogue GPT model on in-domain data. Next, I'm going to discuss our zero-shot slot filling experiments. Why do we expect zero-shot slot filling to work? In Gensf, we have aligned the pre-existing capabilities of the model to the requirements of the downstream task. This alignment may allow us to better leverage things the dialogue GPT has implicitly learned during the course of large-scale pre-training. This includes the ability to understand and generate natural language, as well as implicitly learn knowledge of certain slots, such as things like time and first name and so on. We report the results on zero-shot slot filling on the 5 slots present in the restaurant 8K data, as well as the average in the last row. We compare to Convex, who also reported zero-shot results, and the Coach plus TR model, which has achieved strong performing in zero-shot slot filling on a number of datasets. On several slots, Gensf strongly outperforms the other models. This indicates that our simultaneous adaptation allows us to effectively leverage the capabilities of the pre-trained model. On the date and time slot, Coach plus TR outperforms Gensf. This may occur because the Coach plus TR model was trained for slot filling on other domains. Slots like date and time are more domain-agnostic slots and therefore may be easier to generalize to. In contrast, Gensf achieves close performance to the Coach plus TR model on these slots without any training on slot filling whatsoever. On average, Gensf achieves a 9 F1 score improvement over Coach plus TR and a 4 F1 score improvement over Convex. These results in zero-shot slot filling validate the effectiveness of Gensf and our proposed simultaneous adaptation. To further understand the capabilities of the Gensf model, we carry out ablation experiments that remove the different types of adaptation. When removing the adaptation of the model, we observe moderate drops in full data and few-shot settings. In contrast, the zero-shot performance drops from an F1 score of almost 20 to 0.5. When removing the adaptation of the task, we observe a small drop of 1 F1 score in the full data and few-shot settings. However, in the zero-shot setting, the performance drops to 0. In this paper, we propose Gensf, a generative model for slot filling. We carry out simultaneous adaptation of dialogue GPT to the task of slot filling. Gensf achieves strong performance in full data, few-shot, and zero-shot settings on 2 different datasets. Our empirical results demonstrate the importance of incorporating inductive biases and simultaneously adapting both the model and the task formulation. Thank you for your attention. The paper and code can be found with these links.